Hello and welcome to lecture 5 of this unit, which is determining circuit model parameters. So today we will look at how to determine the values of the various parameters of the circuit model that we've developed in previous lectures. So let's get straight into it. So how do we measure the elements of the equivalent circuit? This is our equivalent circuit that we had developed over the past few lectures, and it shows you the values, or rather the elements that can electrically represent the induction motor properties. So the rotor, the stator, and all those parts of the induction motor that allow it to run. Okay, so we have all the common models that we have talked about, all the common circuits that we have talked about. And we noted that previously we had said that the input power comes in there as an electrical voltage and current at a certain frequency, and the real power that is transferred from electrical into rotational or mechanical passes through the various resistive elements. So R1 represents stator copper losses, RC represents core losses, and in this case, in this configuration, we have air gap power being represented by this element. And the various inductive elements, they were representing the inductive elements of the machine. So each power loss or each transfer is represented by a resistance that has a current flowing through it, and the various magnetizations and reactances and transfers and magnetic fields are represented by inductances or reactances. So now experimentally, if you have a motor, how would you determine the values of these elements just with the motor and laboratory or testing equipment? Usually we have 3 tests that we can carry out that will enable us to determine, alongside with certain knowledge of the physical parts of the motor. We have 3 tests that we use to determine the elements. So those are the DC test, the no load test, and number 3 is the locked rotor test. Okay. And by using these 3 tests in conjunction with each other, you can determine all the elements of the circuit. So the DC test will give you R1. The no load test in conjunction with locked rotor test will give you the magnetizing inductance, and X1, X2, and R2 can be determined from the locked rotor test. And the no load test will also determine rotational losses. Right? So let's get straight into it. Right? So the first test that we will check on is the DC test. So let's start with the DC test. So in order for you to carry out the DC test, you would use the configuration that is indicated there, right? You apply a variable DC voltage with a frequency of 0. It does not change its voltage value with time. And you apply that DC supply to 2 parts of the motor. So now the motor has 3 sets of windings, which are indicated here. Right? And in this case, you would put them into a delta configuration. That is, you connect one end of each set of windings together. You short circuit one end of each set of windings together. That leaves you with 3 terminals, of which you would connect 2 of them across the supply that you have indicated. So this is our test equipment up to here. All right, that is our DC test equipment, and you apply it across 2 of the 3 windings. Now, in this stage, the voltage is applied across 2 of them. The reason why we apply it across 2 of them is that we would want to determine the resistance of the windings as an average of each other. So by connecting it across 2 windings, you can be able to get at any given time the values of the average out of 2 of the windings. So that in this case, the voltage can be shown as VDC is equal to the DC current that is applied times the values of the 2 resistances. If we say each of them is R1, or the average value is R1, you would be, that is the Ohm's law version of that. Rearranging, you can therefore see that if we make R1 the subject, it will be given by VDC over IDC DC times 2. So half of those, right? Simply put, you straight away can get the value of resistance of the stator windings, which is given by R1. All right, so you have the first element of the circuit. Next, we look at the no-load test. So the no-load test, we are now applying a variable AC voltage with variable frequency from a 3-phase power source, right? At the same time, you are able to measure the input power through these 2. You have the 2 watt meter methods of measuring power. You have various ammeters connected along each line, and a voltmeter that measures the value of the voltage that you are supplying. Okay, and what we will find is this no-load test, as we had said, can give you the value of rotational losses, and it can also determine, alongside the full load test, it can also determine the value of magnetizing impedance, right? Now, as we are carrying out this test, the reason why you can be able to measure the rotational losses is that, as the name suggests, no load is connected to the motor. What does that mean? It means that you simply connect the motor directly to power without any load being connected to its shaft. We are talking about mechanical load. The mechanical load that would be applied to the motor is only the fan, cooling fan that comes as part of the motor, and maybe the friction that is in the shaft, right? So the only load here is rotational losses, which are equal to friction and windage. Okay. Now, in addition to this, it will be important to note, remember that in our circuit, if we go back to this, remember that in our circuit, we had 3 resistive elements. You had this one, you had this one, and this one, okay? We have already, in the previous test, determined what R1 is, right? So at the moment, the resistances that we don't know, yeah, the equivalent resistances that we don't know from the circuit are the ones that represent core losses and the ones that represent air gap losses. In the case of the no-load test, the air gap losses, or the air gap power that is provided, is only providing power to rotational losses. So the total value of power that is in this circuit that we don't know of, that is apart from the stator copper losses, is the rotational losses and core losses. Okay? It's important to note that, right? The value of power here would be both the rotational and the core losses that we have. So we'll look at that a bit later. Now here, we note that, as we have said, R1 is already accounted for within the stator. So let's have a look at these rotational losses, or the power that is being supplied as air gap power. So let's call it PAG, right? So air gap power, if you recall, is represented by both rotor copper losses and the converted power. Yeah, so the power that becomes eventually mechanical power minus the rotor copper losses. Now, if we represent these electrically, you can say that the air gap power is given by stator current squared times R2 over S, right? It is represented, as we had seen, by this element, R2 over S. So that element is split into two, which are 3I2 squared R2, which is the value of the resistance of the rotor itself, the rotor windings, and 3I2 squared R2 into 1 minus S over S, which we had determined previously. Yeah, if you recall, we had shown here this split, where you split it into rotor copper losses and converted power, and that gives us our modified electric circuit, which we now have down here, right? So from air gap, you split it into two, and you now have R2 and this resistance here. Okay. So what we want to determine by splitting them like that is the relationship among all of these. Okay. So if you have the no load test, yeah, remember now we are having a variable voltage. Yeah, we can have a lower voltage, and we can have also a lower frequency or a higher frequency, depending on whatever we want to determine. So if we want to run it at rated, we would put it at a voltage that would allow us to do that. Okay. So when you have the circuit connected like this, right, no load is being applied onto the machine. There's no mechanical load on the machine. What does that mean? It means that slip, which is the difference between mechanical speed and synchronous speed, is very, very small. Okay, is very small. Yeah, if we can take it to be a value of 0.001 over, that is the fraction that you would take, right? You can say 0.1% of the as the value of the slip. Okay, this means that because S is small, what happens to this element here? Yeah, so if we say R2 into 1 minus S over S, if we take it as 0.001, which is a very small figure, then R2 into 1 minus 0.0001 over 0.0001, like that. This means that this will be a very big figure. So it will be R2 1 minus 0.0001. Let me switch to show you the calculator. 0.001, like that, divided by 0.0001, and that gives us 9999 times R2. So this means that this element is much, much larger than the value of R2 itself when you are conducting the no load current or the no load test. Okay, so the impact of this, the voltage drop, yeah, if you look at the entire circuit, the voltage drop of this arm here, yeah, where E1 is being applied, the majority of the voltage drop will take place on this element here, such that the participation of X2 and R2 in this case are very minimal. That means that during no load, you can effectively disregard R2 and X2, okay, when you have no load being applied, right, in terms of the voltage itself, okay? So this means that you now have yet another circuit which now looks like this, okay? So you have your converted power, which we said up here is actually constituting rotational losses, and that is represented down here. So these are rotational losses, okay? You have your magnetizing inductance and you have your core losses there, right? And so this now would represent your final modified circuit that represents how the circuit looks like or how the circuit appears under no load test conditions. So what does this mean to us now? This means that if you were to look at these three paths for current, yeah, this one, and that one, okay? So these are three different paths that current could take. So I1 splits into these three. Which of these is most likely to take the most current, okay? We've said that this value is a very high current, high resistance. So it would take a lower value of current, okay? Same with the core losses here. Comparatively, when the load is very low, the amount of current that is being used, the current that is actually being supplied to the machine is very, very low. And the majority of current will actually be used to set up the magnetizing effect, which is XM, okay? And that means that the value of XM is much smaller than these two, and therefore these are generally disregarded, yeah? So you would have XM being the majority, the most current will flow through that arm of the circuit, right? A bit more consideration. Also, if we were to look at the circuit once again, the circuit that we have remaining, where we have these three components, R1, X1, and XM, okay? And this is our phase voltage, and you have a current flowing through, right? A test current and a test voltage, okay? What are the voltage drops across each of those? What we will realize is, because it is no load and because this current is very low, the value of the voltage being dropped by R1 is low compared to the value of voltage being dropped at these other elements, right? And therefore it means that if we had some way of determining X1 and XM together, we can say that V phase over I is roughly equal to JX1 plus JXM, okay? So in this case, remember we said that the no load test needs to be taken in conjunction with the locked rotor test. The reason for that is you can determine XM from this test, right? You can determine the magnetizing reactance from this test, but it is tied to the value of X1. So you would first have to determine what X1 is before you can determine XM. So this is the configuration for your locked rotor test. What this means, what this configuration shows, similar to what we had shown, we are putting an AC that has an adjustable voltage, an adjustable frequency, and it is a three-phase power source, okay? We are still measuring power through wattmeters. We are still measuring current through ammeters. And we have a voltmeter that is determining what the voltage is that is being supplied. What we mean by locked rotor is that we clamp down on the shaft. So the shaft cannot rotate. The motor itself cannot rotate. Even if the rotor has, torque to supply, we put brakes on it so that it is fixed in place. So any current that flows through the rotor does not get converted directly into mechanical load. So whatever conversion takes place, it is not enough to overcome the force of holding it back, the force that is holding it back, right? And this is a key thing to remember, because what you note that the value of the current here, and remember we have an adjustable voltage and an adjustable frequency three-phase power source. Because you have your locked rotor, and because from the point of view of the motor, there is a very, very heavy load that has been applied. What this means is that even if you apply a very small voltage, the current that will be induced in the rotor as it attempts to act against that load, the torque that is being supplied cannot overcome the load. So you just find that the rotor keeps drawing more and more and more current, which could be damaging to the motor itself, right? In practical situations, you have, if the motor locks up, that is why your motor burns out. The windings of the motor burn out because it attempts to draw more and more current to be converted into a power that can overcome the locked rotor, right? Now, what is there when the rotor is locked? Our slip will be 1, all right? Because remember, n equals 0. So ns minus n over ns will be equal to ns over ns, because this is 0, okay, which is 1, right? So that means that if we go back to our circuit here, it means that for purposes of our circuit, this R2 over S is actually just equal to R2, right? So you have all the air gap power that is being transferred is going purely into rotor copper losses, right? Yeah, and your converted power is 0. None of it is being converted into mechanical. All of it is going into rotor copper losses, right? So what does this mean? It means that if we look at this particular arm, all the current that we are talking about will be flowing through X2 and R2. So more of the current will tend to flow in this side and less of it will flow through this arm, okay? For the same reasons we talked about before. This value of R2, remember R2 is very small, right? It is different from what we saw before. So the reactance that is encountered by the current as it splits in here, this reactance is very low. This arm, the reactance and the impedance is very high. So the majority of the current will be flowing into I2. For all intents and purposes, actually, you can disregard this because that impedance is so high, the circuit it has a negligible impact on the circuit. So you would actually end up redrawing the circuit as R1 GX1, R2 GX2, okay? So this is your locked rotor test final circuit, and you have a phase voltage and current I, right? So here in this particular case, you will know that your value of impedance, the ZLR, is equals to phase voltage over the load, which is equal to line voltage over √3 times locked rotor current, right? So this means that our ZLR actually is equal to RLR plus JXLR, where RLR is equal to R1 plus R2 and X RLR is equal to x1 plus x2. So if we look at these two in turn, so RLR, we already know R1. So this means that you can determine R2 from the value of RLR that you will measure from here, minus the value of R1, which you had already determined by the DC test. Okay, so here you can get R2. What we then have with XLR is we use a certain characteristic of the motor, which we call the design characteristics. So the rotor design determines the ratio between X1 and X2. Okay, so if you have, for example, a wound rotor, XLR will be equal to X1 plus X2, okay, because it's a ratio of half and half. But if we take design B, we will know that X1 is equal to 0.4 XLR and X2 is equal to 0.6 XLR. So the ratio is predetermined by the characteristics of the machine itself, or the characteristics of the design of the machine. So those you are able to determine. And by that means, you will be able to now determine X1 and X2. Okay. And finally, one key aspect that one would need to remember, because of the nature of the locked rotor, you will not apply the full rated voltage or even the full rated frequency. If you were to do that, as I had said earlier, you can likely burn out the motor. So usually you will have a reduced voltage and a reduced frequency. So actually your XLR, which will be determined experimentally, will be given by XLR prime, which is your test frequency. And actually XLR over the test frequency is equal to XLR normal or rated at the rated frequency. And that's an important characteristic to remember, such that your rated XLR is actually equal to your rated frequency over test frequency times your test XLR. Okay. So by using all of these various tests that we have done, we are then able now to calculate the values of the various parameters that we had indicated within our equivalent circuit. Okay. So to put this all together, let's look at an example. So we have a three-phase machine that has those characteristics, and we are being shown that it is a design A induction motor, which we have just seen the importance of that. It has various rated currents, rated characteristics that are shown there. And DC or DC no load and locked rotor tests are carried out across the machine, and they give those values that are given there. So we are asked to sketch the per phase equivalent circuit for the motor, which I have sketched there. Now we are told that core losses are negligible, which is why I have indicated that RC, the wing that would have been here, this wing that would have been here, has been disregarded, right? So we will not be taking that into account. But we do need to calculate R1, X1, X2, R2 over S, and so on and so forth. So let's take each of the tests and see what we can come up with from the different tests. So let's bring back the calculator and get started. So straight away, obviously the easiest one to look at is the DC test. So what do we determine from the DC test? First of all, you determine R1, which is pretty straightforward. That is DC voltage over 2 times DC current. And we are told that you've been given a voltage of 13.6 and DC current of 28. So 13.6 over 2 times 28, which gives us so our R1 is 0.242, let's call it 9 ohms. Right, so here we can say 0.2429. Okay, let's get into the no load test. What do we determine from our no load test? We know that our currents have been given, so we have 3 scenarios for the 3 phases. Currents are not fully balanced, but we take the average of those. So no load average current is given by 4.1, 4.2 plus 4.1, 4.1 plus 3.9, and the average of those. So that is roughly 4.0667 amps. Sorry. Okay. Phase voltage, we know what that is, or rather we have been given a line voltage, so we can determine the no load impedance from that. So the no load impedance will be given by 415 over root 3 in order to get phase voltage times your current that we've just determined. So inverse of that times 415 divided by root 3. So that gives us a value of 58.92 ohms as our impedance there. Now, phase voltage is here and current I1 is here, or current is there. Okay. So in the case of a no load test, the value of the current that is being taken through, how much of it is converted into real power. Remember we talked of what is the value of the power that is being given. So the stator copper losses in this case will be 3 times no load average squared times R1, okay, which will be 3 times 4.0667 squared times R1 we got as 0.2429. Okay, so 3 times 4.0 squared times 0.2429. Right, this gives us a power of 12.05 watts. Okay, and therefore our rotational losses, which we said constitute the entire amount of power that is being consumed by the rotor during the no load test, will be the input power minus those SCL that we have given there. And that is determined by input power we had been given as 420 minus 12.05. So this is 407.95. Now looking at our locked rotor test. So we are on the way to determining some of the other parameters. So we now look at the locked rotor test in conjunction with the no load test. So our current for locked rotor as an average is 14.1, 14, and 13.6. So 14.1, 14, and 13.6. Average is divided by 3 is 13.9 amps. Okay, and our impedance with the locked rotor is phase voltage over locked rotor. So we know our phase voltage is in the locked rotor test that we've given. Note that we are using a lower or a reduced voltage and a reduced frequency because we don't want to damage. Remember that this is running at almost the rated current, and we don't want to damage the motor by running too much current through it. So we have 50 over root 3, which will give us our phase voltage, times the current that we've just gotten, and that gives us an impedance of 2.0768 ohms, right? So what can we determine from this, right? Now, a key thing that we would need to determine is the angle. Remember, we have impedances or reactive impedances and resistances, right? So this has two components. So there's the real power components and the reactive power components. So that means that our input power, which we have been given in the case of locked rotor, we know that it is 920 watts. But what is the component of this power? So it is given by root 3 times the voltage times the current, which is locked rotor, times cos of the power angle, right? So we don't know this power angle, but we have calculated this, and we know this, and we know this. So here we want to get the power angle so that we can separate out the resistances and the reactive impedances, all right? So this cos theta will be given by input power over root 3 times voltage times current, right? Which is given by input power is 920 over root 3 times line current, which is 50, times our locked rotor current, which is 13.9, which we are determined here. Okay, so cos theta is given by that. And it is 0.76426. So the cos inverse of that is the value of theta, which is 40.1586 degrees. Okay. So having known that, we can now use this information to come up with a number of things. We know that ZLR is, we know that RLR is ZLR times cos theta. Okay, so we already have ZLR, so we can make use of this to know RLR, which we already determined, and we said that in the previous discussion, we showed that RLR, yeah, these are the two elements that we are looking for. RLR is R1 plus R2, and XLR is X1 plus X2. So those are the two that we are trying to find out. So RLR will be ZLR 2.0768 times cos theta, which is 0.76426. And that gives us 1.5872 ohms. Okay, so remember RLR is equal to R1 plus R2, but we already know R1. So this means that R2 is RLR minus R1, which is 1.587 minus R1 was 0.2429. Minus 0.2429. So this is 1.344. Okay. Similarly, we know XLR. We can get XLR. So XLR will be ZLR sine theta. Yeah, because they are perpendicular to each other. So that will be 2.0768 times sine 40.1586 degrees. So 2.0768 times sine 40.1586. And that gives us a value of 1.339, let's say, ohms. Okay, so we know XLR, and we know that this is the test value of XLR, right? So the true value of XLR, the actual value of XLR, will be given by the rated frequency over the test frequency times XLR prime. This is rated was 50 and locked rotor is 15. So 50 over 15 times 1.339. So the actual XLR will be 4.464 ohms, right? So that is our full scale XLR. And because we are told this is a design A, we said the design A type of motor has what ratio of X1 to X2? So it is that they are in a ratio of 0.5 to 0.5 or 1 to 1. So each of them is half of the value. So X1 is half of that. So divide this by 2. That's 2.232. And at the same time, X2 is 2.232 as well. Okay. And remember, we said that we can use now, because the only one that's remaining is XM. And we said we can use the identity that in the no load test, yeah, in our no load test here, we will know that the phase voltage over the current, which is the Z no load, is given by X1 and XM. So we have just calculated X1 here. So we know it is this, all right? So XM will be equal to X no load minus X1, right? And X no load here we knew is 58.92 minus this 2.232 that we've just gotten, which in turn gives us 56.688 ohms, right? So we have actually determined all of these. So we know that XM here is 56.688 ohms. X1 and X2 were given by 2.232 ohms, 2.232 ohms, 2.232 ohms, and R2 over S, we got our R2 here, which was 1.344. So it is determined by 1.344 over whatever the value of slip is at that particular operating. And therefore, by that method, we have then determined the entire characteristics or the entire values of the equivalent circuit for all that machine. And we can stop there.